Welcome to Artificiality, brought to you by the founders of Sonder Studio. Artificiality is a podcast dedicated to understanding the emerging community that is humans and machines. We take the latest in the human side, decision science, psychology, and design, and put it together with advances in artificial intelligence and big data so that you can understand how to work better with machines and your fellow humans. We founded Sonder Studio to help people be more human in the age of AI. We're on this learning journey too, so we strive to find the frontiers, to ask the best questions, and stay curious. We interview some of the top minds working at the intersection of humans and machines and make sure we have a few laughs along the way. Have you ever wondered what it means to be data literate in a world of big data and AI? Now that so many decisions rely on information that is only readable by a machine, and our statistical intuitions, which were bad before, are now practically useless, what is data literacy in the age of AI, and how important is it? We talked with Jevin West, professor in the Information School at the University of Washington, co-founder of the DataLab, director of the Center of the Informed Public, and co-author of the acclaimed book Calling Bullshit, to ask these questions and more. Jevin, thank you so much for joining the podcast. We're really happy to have you here.
Thanks so much for having me, Dave and Helen. This is going to be a lot of fun.
Excellent.
Cool. Well, one of the first thing that comes to mind for me is just first of all, congratulating on Calling Bullshit, because one, what a great title, and both the book and the series, and highly recommend it to all our listeners. I loved watching the series, but the thing that really grabbed me about it, the thing that made me think so much more, is in this age of AI and big data, in particularly, how does that change data literacy? Does it make it more important? Does it change how we should approach it? Does it change the definition? How do you think about it?
I think it makes it even more important to be doing our best to make people aware of the ways in which the technologies that envelop them each and every day are working. Because at the root, it's not as complicated as people think. And if you understand, for example, that most of these algorithms are based on a training data set that anyone can interrogate, that anyone could ask questions about, anyone could start to see some of the limitations and also the potential of these technologies. So I think data literacy is more important than ever now, just because data is found everywhere on our Facebook posts, in the news, when we're talking about the pandemic, when we're talking about the newest self-driving car. It's everything we do. But I think education in this space is just beginning to catch up. I wouldn't even say catch up. It's just starting to really get going in this space. So I think it's more important than ever, given the world that we now live in.
One of the things that strikes me is that we talk about that humans, we're cause and effect beings, right? That's our sort of native language. It's how we understand the world around us. That's how we communicate with each other. But machines are correlation entities, things. And does the world of correlated data conclusions increase the ability for us to be bullshitted?
Absolutely. I mean, just as you said, it's both a strength and a weakness of our cognitive capabilities. It's like a crutch in some ways, and in other ways, it's very useful. There's real advantage to be able to have a software system that we depend on in our brain that looks for those causative explanations for where to find the best food for the night, if that's what you need, or to make sure that you don't, get hit by a fallen tree or something. I mean, there's real advantages to that causal machinery that we depend on, but it can get in the way a lot when we're dealing with data and with scenarios where there's lots and lots and lots of inputs. And many times those inputs are just by chance correlative, and that can get us into trouble. I mean, just to give you an example of even how professionals can get in trouble, there was a paper that was published in PLOS, a couple of years ago, that analyzed the 50 most shared health news stories in social media. And of those 50, half of them misattributed causation for correlation, which it was correlation, but they were writing it as causation. And that's, of course, the onus is a little bit on the journalist. But even worse than that, a third of those articles were misattributed by the researchers themselves. These are trained researchers always being told to look out for correlation causation. And these are the 50 most shared ones. So these aren't even all the others that probably there are less inquiry on those data sets. So it goes to show that it's everywhere. And when I talk to students and I start saying, okay, we're going to talk about causation today. And they go, okay, correlation doesn't imply causation. I know that. And then I'm like, okay, let's do some tests of your ability to identify that. And they struggle, really struggle. And it's not that they're not smart. Students are incredibly smart. It's just that it's something that we have to work harder as humans that are always looking for causation. And so, these discussions have been around forever. There's Latin terms for this. Post hoc ergo propter hoc is this Latin term that says just because something comes before doesn't mean it causes something after, yet people fall for this all the time. So it's just something we just have to be a little bit more aware of, especially with all the claims that are going to be made about causation, because that is the sort of the thing that we're after a lot of times. And really in research, there's the only way, well, there are some ways, but the golden standard are like random control trials. Well, guess what? 99% of the time, right? I'm just making up a number there since a person that questions numbers all the time. But a lot of the time, you're not going to have the ability to do random control trials or have natural experiments or pseudo random control or these pseudo natural experiments. So if you don't have an RCT, then you have to, you have to be pretty skeptical of what you're seeing when you see causation claims.
Yeah, we see this a lot with people struggling to get their head around how to make decisions when the data set is really complex and really big, and there's a pattern. But that pattern, it's not clear. So there's this motivation to find an explanation, but there's almost you construct an explanation. It's yes or no satisfying. Then you've got to actually act on that. And this process of sort of getting sure enough in something to act becomes so much more complicated without this causal story, and yet it's harder to actually pull that together and be really sure. So, like you say, you can imagine your student struggling with it, because on one hand you're really motivated to sort of find a cause, but on the other there's this little voice on the shoulder saying, don't overthink this, or don't overfind patterns in the data because they could be random. And that's something that, like in your research and the book, kind of blew me away, is just how often we could just be finding random patterns that then we're motivated to find a causal story around. And then that story becomes really powerful. And how do you coach those students through that difficult process?
Yeah, it's a really good point. And I certainly encourage students to work towards that causal explanation, because most of the students, at least in the computer science, really are just about, hey, look, the predictions are going well. And then you say, okay, well, how is it doing a year later? Because of the bugbear of machine learning, which is this overfitting tendency, because of these patterns that will exist just by chance a lot of the time, especially as they get bigger and bigger and you add more and more variables, you're gonna find these patterns. And so we have to be careful. And it's having this idea that we're talking about of these sort of happenstance correlations and patterns that you find is affecting sort of even some of the knowledge production in science. So, because if you're using p-values and 1 out of every 20 times you're going to get something that is actually not, linked and it is not, so we'll just call it true, then that can lead to, a sort of a skewed view of reality, because we're like, hey, it's p-value, but if we're only publishing positive things, it also gets at this as problem as well. So even science, so I'm saying like individuals are susceptible to this, but even science as an institution has been somewhat susceptible to these things as well. So I guess that should get everyone confident that, okay, even if science, which I'm a huge fan, and despite some of its problems, still is one of the most amazing human inventions, it works really well. And the other problem is that we want to have answers. We want answers to be in certain ways, and we want causal links a lot of times. I mean, I'll give you an example. Just in COVID, there's so many examples, but one example during COVID of a story that went viral, and many of them, we have many, when you're studying these kinds of things, you have hundreds and hundreds of examples, but one of them was a claim that there was a link between those men that are bald and people that are susceptible to COVID-19. And it was published in a fairly reputable clinical medical science journal. And its claim was that there was the androgen pathway that's associated with baldness was also associated with COVID, and had this big explanation. And it got reported in Forbes and all these other major national journals, and it went viral. But they forgot one important problem, and that was that there was a likely other common cause. That there wasn't a direct link between if you're bald, then that's going to lead to COVID susceptibility. It was that age, very simple, age is probably a common factor in leading to someone being more likely bald and also more likely to be susceptible to COVID or death of COVID. And so when we want to know an answer too, it's even harder. So we're like, oh, this is a good story. Oh, I'm going to share this. Look, I'm bald, or my friend's bald. Look, and then this is sharing before anyone sort of dug in. So it's this human tendency to, want to see these patterns. Now, it doesn't mean we shouldn't go after those causative explanations. It's just really hard, and we have to be very cautious, and we have to hit the problem in multiple ways. And most importantly, we can't just depend on machines and the powerful techniques they have to do the work of causation for us.
Yeah, I mean, we have so many other conversations we could have about something like just automation bias. But when you put automation bias on, this machine's figured out the cause, and position that as the answer, I can see everything just like amplifying even further. And what about when you're taking people through the very early stages of, say, building a machine learning model? What's the practices that you set up right? And because you mentioned training data and people being able to interrogate the training data, what do you advise them to do when it comes to really understanding that training data? We see a lot of instances where people go, "Oh, data, let's just all put it together and see what happens." But that doesn't feel like the right process. It feels like you should start right at the beginning with these critical thinking processes.
Absolutely. So if you could allocate a percentage of your attention, and you could say, okay, I'm gonna grab 95% of your attention. I'm gonna have you focus not on the details of how the algorithm works. I mean, there is importance in knowing something there. But if you're talking to the general public, and the general public, by the way, can understand the core concepts of machine learning fairly straightforward. You don't need a PhD in computer science and statistics to know the most important parts for at least calling BS on some of the technology. I don't expect them to know the intricate details of a deep neural net or something, or the new technology, GPT-3 or whatever. But I do want them to know that at least in the supervised realm, we can just jump straight to the training data, or at least interpretation of the output of that. But let's just focus in on the input data. If you just focus on whether it's a representative sample, where did it come from? How were the labels, the ground truth labels assembled? And here's the thing, just recently, a couple of weeks ago, there was a major study that came out at MIT where they looked at some of these well-trodden image data sets for computer vision. These are data sets that are used for training computer vision algorithms that are used everywhere in self-driving cars, in sort of facial recognition technology, you name it. And these data sets like ImageNet and others, some researchers have found how many problems there exist in those data now. And we've been using them, the field, for years and years and years. And now we're finally inspecting those and finding, wow, there are lots of errors, which then are propagating through to some of the predictions. And again, it doesn't take away from the powerful predictive capability of these algorithms. And there are certain situations where you actually don't care about causation, that you're okay with just simple predictive capabilities. Like if you're REI, all you care about, I mean, you don't care necessarily why. I mean, in some ways you might be, if you're an economist, care about why someone buys, hiking boots and, Nalgene bottles on the same day. But really, what you're going to do is, as the retailer, you're going to put them together and make sure. I mean, insurance agencies are another example. I mean, they don't necessarily need to know why. They just need to know that, that people that drive this type of car in this region at this age and this, whatever, those are things. There are examples where you just care about prediction. But when you're talking to the public about technologies, let's say, that are, trying to determine whether you should be convicted or not, or you should get a job, or you should get insurance or mortgage or these things, talk to them about the data that's being used to make those predictions. And by doing those kinds of interrogations and having discussions around the data that's being fed into those algorithms, anyone can do that. I mean, middle schoolers can have discussions about whether that would be representative or not. And there you've gotten like 80% of the way there about finding the sort of BS. Because when I look at all the hundreds of journal articles and research reports and proposals that I've had to critique and review, so much of the time it's not within the black box. Once you've sort of worked out how to work, how to run a random forest algorithm, it's not that you don't need to know some of the details. There are problems that can occur there, and you need to know them to do some more of the interpretation. But again, most of the time it's when someone makes an error on the selection of their training data. So the whole point is like, hey, anyone can do this. Anyone that's had no training in computer science can start to question, some of the technologies that we're using all the time.
I love your example of the of ImageNet. One of the examples that we use in our workshops is a screenshot from Kate Crawford's project.
Yes, Kate, right, she's actually going to be speaking in our center, I think, next week about her new book. So
okay. Well, you can tell her that we use I use the their little project and put it on my phone, and I've got a screenshot of it that we use and we show that has me smiling at the camera, and it labeled me as a creep and a weirdo.
Oh no! Well, Dave, I mean, I was going to accept this conversation, but now I don't know. Maybe we should.
Now I don't know. and we weren't sure. I mean, it's what the thing that we try to tell people is it's unknowable why. Right. We don't know because these things were labeled over many periods of, over long periods of time. We did talk to somebody who was early on the Watson team whose hypothesis was that the images, that a lot of those ImageNet images were labeled right after 9/11. When there was a priority of looking for potential terrorists, and potential terrorists tend to have facial hair. And so there was some connection that I, smiling with my, limited facial hair, came across as a creep and a weirdo. But the problem, of course, like we talk about is the problem is you can't interrogate it. You can't change it. If, one of our kids' schools was using this as a security system, I might get flagged as somebody that shouldn't be allowed in, right? But that's that example. So I love that you use that because that one example, you can see people's eyes light up and go, oh, wait, now I understand. Images go in, they get labeled. We teach the machines with our labeling in the training data, and out comes some answer that we can't explain necessarily.
One of the things that worries me about a little bit about sort of the growth of low and no code AI ML is that people miss the fact that you have to really understand the training data, and you can just drag and drop, and suddenly you've got something that's highly effective from a prediction perspective, but end to end, there's absolutely zero kind of visibility even from the person who builds the model. I mean, normally the person who builds the model learns the most, right? But if you're not really hands-on and crafting, do you lose the sort of motivation to even really craft at the front end of the process? Or do we somehow manage to shift people's mindset that actually going and looking at the data and understanding the data is a really valuable and important thing to do? It almost feels like the incentives are on the end of the process, not on the beginning. You're a hero if you produce great predictive outcomes, but you're not a hero if you really understand that data set.
Totally. And it's partly because that's the boring part, at least to most people. If you look at the scientific literature and those that get cited and the accolades that come, it's who comes up with the next method, the next permutation on the algorithm, the person that produced the nice application, the person that, was reported on by the journalists because they're the ones that sort of, took the algorithm into the public or whatever. But all of this depends on the data that was used to train the algorithm. And that's the boring part. It's the hard part. It's the time consuming part. Yet it's the most important part. And it's the part that we can all get, involved in. And maybe one of the, cultural improvements, at least in the research field, would be just what you said, Helen, would be to sort of require that there is an engagement by the technologists and the computer scientists that are doing the theory building and the algorithmic building, that they engage with that training data or do some audits themselves. Although you could have an independent group do that, and some are starting to do that already. But again, it's overlooked so often, and the fame comes to the algorithm. But what's interesting is a lot of the algorithms, even used today, even despite this huge acceleration of neural nets, the algorithms like k-nearest neighbors and naive Bayes and all these algorithms that have been around for over a half a century, the algorithms themselves are not that complicated. They're pretty straightforward. Neural nets are kind of a different ballgame. There are other algorithms too, but many of them that are still used today and quite effective are quite simple. And they're though even those could be explained pretty easily to the public. But again, you don't even need to go there. The training data is where we can go, so we can try to understand why Dave is a freak or whatever the label that we're giving it next time it runs it.
Well, it's a brave person that says the algorithm was right.
Yeah, right. Yeah.
Or perhaps the brave wife who says the algorithm was right. So I want to flip to the other side of it, if I could. We've all gotten over the last couple of decades, I guess, of the pervasiveness of Excel, we've gotten used to bar charts and line graphs displaying results of basic models, if you will, financial models and those kinds of things. What does it change? How does AI change visualization of data? So as we think about something that comes out as a prediction, when we don't really understand what's behind it, we can't, or it's at least in the bar chart, we don't understand what's behind it. How do you think about changing the nature of visualization so that we understand more about what's behind that prediction?
Well, I think it's a good question, and it's one that would require sort of a way of being a little bit more transparent about what's happening underneath the hood. So if you take, let's say you're trying to predict breast cancer from a whole bunch of different variables of patients that came into the hospital. One of the things that you could do is that you could, instead of just looking at whether the newest patient is predicted to have breast cancer or not, you could also look at the way in which the algorithm was trained by looking at the correlation between the individual predictor variables. So those are all the different variables it's using to learn and make this prediction of whether someone has breast cancer or not. And that could be, the size of a tumor, or it could be, all sorts of different variables. It could be the blood pressure of the patient, all these things. And then when you look and see whether there is correlation among those variables, you could then say, okay, some of those might be real, some of those, and a lot of it's, you'll see this anyway with most problems as you get more and more input variables, it's just by chance, you're going to start to see redundancy in the information used to make predictions. So in that case, you could reveal some of those variables that are highly correlated and to see whether there is even just real information contained in those. The problem is it does get, when this data gets pushed into into the black box, it's not always straightforward what's being used, especially with neural nets, which is, a lot of what's being used today. But in terms of visualization themselves, but even if you just put, the visualization of AI and its underbelly, and you could even just say, that we should make sure that at least the representation, assuming the data is good in and of itself, that we don't violate things like the principle of proportional link. Carl and I talk about this in the book, where the numbers that are being presented have to correspond to the ink being devoted to those numbers. So with bar graphs, for example, many times, often, we see these all the time, where the ink devoted to a number, an actual number, like let's say the results are 5 and 10, a lot of times the ink devoted to that representation in that visualization doesn't correspond at all to, one being twice as much as others. Sometimes it could be 20 times more if you counted by pixel level. Sometimes it's 1,000 times more. So just making sure, one way that AI could help, and actually we're doing this as one of many research projects, trying to identify, auto-identify when there's these violations of the principle of proportional ink. So there's even just things on the final end, assuming even the data is fine. But in terms of visualization, the results of machine learning, innards and outputs, I think that's a whole area that we could explore more to help the machine learnists and those using these predictions try to understand better what could be going wrong. There's a lot of potential there on the research, a lot to be done there. And I would also say that a lot of the data that's being used, like large networks, for example, the output are these sort of spaghetti-like graphs. In fact, I do a lot of this. A lot of my work has been in the network science area, which is, has a lot of overlap with a lot of the, at least unsupervised machine learning work that's being done. And there isn't a great way to visualize these high-dimensional data sets. It's very, very difficult. And so what the field does now is they do a lot of dimension reduction. So they do things like principal component analysis, which brings all this high-dimensional data into like 2 dimensionals and these principal components. And there's lots of other nonlinear methods for this that you can, you can start to look at the data in these other dimensions. And that's actually has some real strengths. Because now you're confining it to a 2-dimensional graph that humans can actually deal with. And I think there's some real advantages there, but there's disadvantages too. So this is an active area of research. In fact, there's researchers that devote their entire careers to ways of better visualizing data, to visualizing uncertainty, to visualizing a lot of the challenges that we have in presenting all this data that seems to be everywhere, coming out of our ears. There's so much data. And so, there's a real need for advancement in that area. And we're investing in that in our department. We're hiring faculty that this is what they do 100% of the time.
It's fascinating because if you think about, consolidation of dimensions, right, as you're talking about, a very simple form of that might be, it's a little bit different, but I'll go for it anyway. You take the accounting, output of a company. There can be hundreds or thousands of rows in terms of different types of expenses, and it all gets consolidated down to 3 levels of operating expenses on a public statement: sales and marketing, R&D, and G&A. And everyone who looks at the statement knows what that consolidation represents. Yep. So you could dig into it and you could guess that the salesperson's salary is here, and trade show expenses there. But when you're talking about this, where there's a unique analysis using more dimensions than would ever show up in an accounting program, and the consolidation therefore is unique, it makes it very difficult for someone who's looking at that consolidated output to know what the consolidation represents.
You can't see through the simplification.
You can't see
anymore.
through the simplification.
Yeah,
I guess
exactly.
That's a way of saying what I was saying.
No, exactly. And it's a really good point. And not only it's hard to see what it says, there's almost no way to compare not only to, let's say, another the but even the same data, but maybe a month later, it's so hard to tell, because that oversimplification, again, has its advantage, but it runs into this exact problem of interpretation.
That it would also must make it much harder to spot a duck.
Yeah. Oh, yeah.
And you probably want to explain the duck.
Yeah.
But I look at some of these high, they look beautiful. Some of these visualizations, they're just fabulous.
They are.
But I have no idea what half of them mean.
Oh, totally. It's all eye candy. And actually, ducks is a favorite term of ours. We use it in the book and the class. And it's this the idea that you sort of put sort of presentation or design over sort of the practical communication of that data. And I think, USA Today has made ducks famous. This is like, if you're trying to show the number of people work out in the United States, you have sort of, instead of just a bar graph or something simple communicating the data and showing what it means, you have like a person on a rowing machine and then the numbers built in, but you can't interpret a darn thing of what it's saying. And so again, they're eye candy, they're catchy. Sometimes they're effective. They're not always not effective, but they cloud the argument that's trying to be made in service, again, of design over form. And so the reason why they're called ducks is there's a famous building, there's many of these, that was, it's a big duck that, looks like a duck selling, ducks at a, I think it's in Pennsylvania. Is it Pennsylvania? Well, there's some duck buildings in Pennsylvania. Architects use the term really first, or at least the idea, maybe not the same term, but but this big duck building that sells, there's only a tiny bit of space to sell, to actually sell the equipment, but it's, again, it's form over function for sure in this case when it comes to data. So we have to be careful of that. We also talk about glass slippers and all sorts of other data problems to be looking out for. But we as humans are great, very strong at pattern recognition, and visualizations can be highly effective. So if you do a good job and you do overcome some of the challenges of presenting data, it can be so effective. And there are a lot of people that have written about this. There's great designers out there. It's just that with the increase of these information visualizations, because people know they're so effective, there's just lots and lots of things now to look out for.
And they're a lot easier to do.
Well, and the tool vendors keep adding yet another, way to show off a donut chart or something else really ineffective,
exactly.
But they make it really easy to make bad visualizations. Yeah.
Totally.
Yeah.
I mean, yeah.
We're on a bit of a mission to sort of point out a few of those things. So I think you got us quite inspired on that.
Yes, definitely.
Well, that's good, because people will start, when we should talk to the students about this, they come up with, the next day in class, they'll come running up and show us all these good examples they found. They're everywhere. And again, in a lot of times, just from honest mistake, or again, this sort of prioritization of, form over function, but it's not, it's very rare. I mean, it is sometimes nefarious. I mean, don't get me wrong. We've seen many examples during the pandemic where I think it was a little bit more than honest mistake. But I think that we just need better training. Even the automated systems in which we depend on that create these graphs, whether it's in Excel or Tableau or you name all these, all the software that people use in business and technology and any industry, a lot of times they'll make mistakes. And an example was the Georgia Department State of Health was receiving a lot of criticism for their messaging during the early parts of the pandemic. And they were putting out visualizations all the time showing sometimes that, there's really been no big difference between time period A and time period B. And then you look at the visualizations and they were showing heat maps with bins that were completely different from one time period to the next. So there's really no way of comparing if the bins that determine the color and the shade of each county, if they're changing, then you're not comparing apples to apples. And so, sometimes, and to their defense, by the way, that it was because the software was automatically doing that. Although, in not their defense, I would say they should be looking out for that. So we all just need to be better trained in that, because the visualizations, again, highly, highly powerful if they're done right. But there's so many different mistakes, even from the software that's creating that. And they're getting better. I mean, these companies are starting to build these checks into these visualizations, but they're coming out every day, bad ones.
It gets much more. The sort of problem gets compounded when it's an algorithm that is running on some sort of continuous basis and coming up with new answers.
Right. Exactly.
And so the visualization may not be accurately presenting the answers from month to month because things are changing, and the algorithms are not great at figuring out how to visualize. Although that'd be quite a technical feat, is to create an AI that can look at a visualization and tell whether it's actually telling the story right or not.
Right, and that's where humans are still so much. I'm always finding ways in which humans can outdo the machines. Yes. The machines outdo humans in so many ways. That's what machine learning can do so well, is it can take into account a lot of data, a lot of things going on at once that humans can't do. But the humans can do a lot of things too, and that's one of many good examples, Dave, which is that, if you were to show a visualization and say what's wrong, good luck, computer vision, researchers that can do a lot of things like build self-driving recognition systems, trying to figure out why a visualization is wrong. That's something humans do, relatively well, whereas machines, don't do a very good job. But there are things that the machines can help humans. They can complement humans' capacity for these things by doing things like, representing uncertainty better. We sort of just kind of mentioned that a little bit. There are researchers out there that have been working on developing new techniques for showing the user, the reader of that visualization, where the uncertainty is. And with any problem, or most any problem, let's say, there is uncertainty. And that's not what's conveyed in most visualizations. It's just like, here it is. But there are good examples. I mean, even if you look at, something that people look at every year during the hurricane seasons, are these predictions of where the hurricane goes. There's, if we could kind of take those ideas that have been developed in meteorology and climatology about making these predictions, because people see those and they kind of know, okay, so the path of the hurricane can go this way or this way. It's not fully certain, although actually a lot of the public still misinterprets those. But I think the vast majority of the people do kind of understand there's all these possible routes. We don't know for sure. But we don't do that kind of thing for most other things that people see. And I think even just like looking at COVID, for example, our confidence in these models of what COVID counts are going to be, a month in the future, we have some, there's these models that are sometimes pretty good, but there's a lot of uncertainty still in those. And I don't think that level of uncertainty is conveyed very well. And that can lead to misunderstandings of whatever process you're looking at, and also can lead to bad decisions. So it's an area that needs to continue to be researched and developed. And that's going to go hand in hand with HCI researchers, human computer interaction, and those that are doing straight machine learning and artificial intelligence.
And psychology and neuroscience and behavioral science and all of that side as well.
Right.
Yeah. And it's interesting when you talk about it, because it does sound like there's a couple of different tensions. So on one hand, it's easy to say, well, humans don't really think very well and probabilistically. So you can show someone something that's Bayesian and they sort of scratch their heads. Dave scratches his head like all day over Bayes, but
it confounds me.
Yeah, I mean, it is.
Me too, and I teach this stuff, and me too.
Yeah, it's not especially intuitive for sure, but then there are great examples, like you say, but there are really good examples from AI, from the AI field, of being able to get an algorithm to show a degree of uncertainty, like this is the certainty over my prediction, but this is also the uncertainty over my prediction, sort of like flipping it around and having the other side show as well. And people kind of get their heads around that. It is actually quite intuitive, as long as it's presented in a certain way, as long as it's not too wide, or as long as you actually really understand what that probability represents. And like for the weather forecasting, as an example, that one's quite difficult. If it's like a 70% chance of rain, is that like, how do you really understand what that 70% means?
Is it 70% at any given time? We just sort of say 70%, but we don't that's not usually discussed as much as it should, because we are usually, when creating these kind of uncertainty measures, they're not always conveyed very well.
Well, we don't have the ability to go back and check, that prediction again and again. So you tend to say, well, it's 70%. Weather person said that it was going to 70% chance of rain, and if it doesn't rain, you think they're wrong, right? There's a binary judgment of the prediction rather than some sense of understanding of, but that still meant that there was a 30% chance that it wasn't going to rain. So the 30% side of it was correct. I guess.
Exactly.
You get stuck in a loop.
That's exactly.
Or that it was just useful enough to know how to plan your day.
Yes.
It's so perceiver dependent in that respect. It's like, what is that? What did it mean for that person to take that prediction?
Yeah.
But I think it's fascinating when you think about like all of the things that are going on under the hood with particularly neural nets, and how that uncertainty gets expressed to a user, because sometimes it depends on the stakes, right? So if you're the doctor making the decision on whether to bring someone in for that biopsy, what does the machine do and what does the human do when it comes to making that decision? And it feels like we're really early days at understanding that interaction and that handoff from what a machine's good at, really picking up, really sensitive, versus what the human's good at, which is, like you say in the visualization, being able to pick up things in a really specific kind of way, knowing that that's wrong, like immediately knowing that. It's just that classic know it when you see it. I know that's wrong about that prediction.
Yeah, totally. I think that's where a lot of the potential is complementing the strengths. And there are strengths that humans, of course, have relative to machines, but also there are strengths that machines have. But, understanding how the machines might influence that doctor's decision, and also how, the doctor's ability to understand local context and human, and just reading the human that's being diagnosed different than what the prediction or the machine's predictive capability, which is on all these other patients that might not be taking into other variables that are in the doctor's room at the time. And but that is where there's, I think, real complements. It's trade-offs. It's like there's trade-offs everywhere in machine learning. In fact, I think it's one of the big lessons that I try to convey with students, that machine learning is about trade-offs. One of the big trade-offs, of course, is whether how important it is it for you to build a model that's incredibly rigid or incredibly flexible? Well, there's advantage in making it flexible because it's going to sort of grab all the sort of patterns it finds, but then you're pushing it into overfitting possibilities. But then if you make it too rigid, rigid is good. It helps it generalize and doesn't get sort of influenced by sort of noise and sort of strange things that might be happening in the data itself that have nothing to do with the actual data generating process. And so there's trade-offs everywhere. And the same thing with human capabilities. And
I was going to say, it sounds like you're describing parenting.
Yeah, exactly. Yeah, totally.
I'm wondering, in your whether it's in the class or elsewhere, how do you help people understand confidence levels that come out of algorithms? So we work with people in thinking about how to make decisions, and one of the core steps in it is understanding how confident you are in your prediction, and whether you're exploring something that you might not be very confident in, right? It's totally like you're just going to go take a bit of a flyer and try it out, versus you're exploiting something that you really, really know. You're really confident in it. I've walked this path 6 times. I know exactly how this is going to go. But there's something different, I think, between understanding the confidence when a human presents something to you. We have a tone of voice, we have body language, we have you can sense someone's confidence when they're speaking. But a machine shows up with numbers and something represented in pixels. Do you have any tricks for helping understand the confidence that a machine gives out, rather than, or is it just looking at a percentage number that says it's a 60% confidence?
Well, I think you're hitting on a whole open area of research that is being done and needs to continue to be done, because this topic, which might seem to some to be seemingly simple, this just representation of how confident we are, is actually really difficult on how you both determine that and how you represent that and present it to the public or to the people that are going to be consuming it. And with humans, like you said, there are cues that you can use, although you can be hoodwinked by some of those cues. So at least machines aren't doing that. But machines, it's not so easy to represent, confidence in a result. Look at even science, for example. The p-value is this, this like target that's used in science all the time. And so many scientists themselves misinterpret p-values. It's one of the most misunderstood and misused a lot of times, statistical measures for determining whether something either should be published and deserves the statistical significance, ribbon. And if we're struggling with that, actually the American Statistical Association several years ago had to come out and basically write, this perspective on p-values, because it was being so misused and misinterpreted. So if we're struggling there, we're certainly going to struggle with these more sophisticated, ways of presenting uncertainty. So I guess to answer your question, Dave, I think we're in the early stages of trying to figure out both how to represent it effectively, how to visualize it, how to communicate it. I think it's, it's not that we don't have ideas. Statisticians do this all the time. Computer scientists do this all the time. But I think given now these new techniques that are used with neural nets and the ways in which we've found mistakes in how we use these large training sets for entire fields of research, it shows that we have a lot to do. And certainly, even aside from all those more under the hood kinds of methods for determining how certain we are in our results, we then have this communication to the users themselves, which has a lot of work. And again, it's a very active area of research in human-computer interaction. In fact, there's entire conferences devoted to some of, well, I would say the entire conference is devoted to information visualization, but even of those subcomponents of, hundreds of researchers that think about this all the time. So it's an important problem that you're painting on. And when you ask what are the tips, well, I think the tips are just starting to emerge when it comes to at least the more complicated forms of machine learning that right now just sort of present, here's the number. Yes, make a prediction on whether I'm going to turn right at this, what seems to be a stop sign or not. There are some things that are a little more straightforward than others, but it's an area we need to be thinking more about.
It certainly expands the definition, I think, of data literacy. It's not just statistical literacy, which, by the way, was hard enough. It's a whole area of design literacy, understanding what story someone's trying to tell, what angle are they coming from, how do they see you as the audience. There's just so many components to data literacy beyond understanding, Simpson's paradox or whatever. And how are you evolving what you say to your students about what it even means to be an AI engineer or a data scientist? It feels like data scientists are being told they have to do so much more, but at the same time, it's an interesting sort of cultural phenomenon to see how data scientists positions themselves in this problem-solving funnel, if you like. They become the problem solvers.
Oh, for sure. I see kind of two kinds of data scientists that come out of our programs and that I see sort of in the wild out in industry doing this kind of work. There's the data scientists that really, know quickly how to take a data set, clean it, to, pick the algorithm to run or pick a series of algorithms. They run it, they do the prediction, they present it to their managers, boom, like that. And that's an important skill set for sure. We need data scientists to have programming skills, that we need them to be able to execute these algorithms as they should be executed in the proper data situations, et cetera. Then there's the data scientist that sort of relies now on more of the sort of push a button on Azure or on AWS, these built-in systems where you don't have to do any of the sort of ground up kind of coding, as much ground up coding that I used to do, even 15 years ago. But that data scientist might be a little bit more interrogative. They might interrogate the data more. They're a little bit more critical of the data coming in. They're taking more time into understanding the strengths and weaknesses of different algorithms, that are asking questions about the output that's coming, that spends more time on the critical aspect. And of those two data scientists, it's the one I just mentioned, the latter, that's doing more of the critical thinking. I think is the real value to industry right now. If I was hiring for a data science team, you need both, but I would certainly want some of those individuals that might not have as much technical prowess as some of them out there, but make sure you have a balance of those that really are critiquing. And I've seen this even in the classroom. There's those students who are always asking questions, where the data came from, like the result seems too good to be true, or something's wrong with that. And those are the ones that I would want leading the teams. And so when people that are thinking about being data scientists, or maybe they're already, certainly your skills should try to span both those kinds of worlds. But it can't be isolated to just I'm plug and playing. They need to be more and more nowadays, especially because a lot of the technology is being commoditized. It's like just push button kind of stuff. So we need them even more to be aware of the ways in which data can mislead as well as it can inform.
Well, that's kind of the core of what we try and do. Mm-hmm. A closing question: if you were going to offer two pieces of advice to AI designers, what would they be?
Well, I think very much always recognize the human that's going to be both a test subject in your data. So being aware of the ways in which data can mislead. And so being, of course, critical of the data, just as we just ended in the final note, which is knowing the ways in which it can mislead as much as well as it can inform. And also sort of recognize the role that, they're playing in society. Anytime you're deploying these things, have that humanistic, hat on at all times, understand the implications of what they're doing, because we've seen those and they can be great too. I don't want to sort of knock down all of AI. And I know I have some colleagues that are, spend most of their time, critiquing and for good reason too. But I'm one that also, would like to, recognize a lot of the great things that can come from a lot of this technology, but just recognize the human side of the technology that they're building. And in doing that, it will help, first of all, build better design. Maybe they'll make more money that way, but also to do it in a way that really takes into account sort of the ethical considerations that are that need to be considered, because we have lots and lots of examples of where that wasn't the case. So I'd say go do great work in AI, but be aware, but then also be quite critical of the data that's coming into your algorithms. I know that's the boring stage, but that's the stage that we should be spending much more attention on.
Jevin, thank you very much for your time. We really appreciated talking with you today.
Yeah, thanks so much for having me. What a great conversation, and good luck with the rest of the podcast series. So thanks, Dave.
Thanks so much.
Solid state.